All right. Good morning, folks. So real quick, I originally intended for the first exam to go up probably before right now, um, but it turns out I actually don't know everything I thought I knew about how to get the lockdown browser stuff to work properly. So I'm going to delay that a little bit. Uh, Hopefully, I'll get it up for tomorrow. I'm waiting for some guidance from somewhere else, and I'll probably have the exam due. Uh, Probably the end of the weekend or even Monday. But either way, it'll go up. You'll have at least 48 hours of time before it's due. But just be aware that it's not up yet, and I apologize for that. But I thought I knew what I was doing, and it turns out I don't. So I need to make sure I have the tech stuff straight before I unleash an exam that's broken on you guys and cause mass chaos and confusion. I definitely don't want to go there. In any case, uh, where we're at right now is the other day we learned about friction and specifically how we were going to model friction, but we haven't had a chance to work a lot of problems involving friction. So we're going to do that. We're going to learn how to deal with friction, and then we're going to learn how to deal with some other forces that are similar to friction. Um, and that's going to be our continuing extension of what we learned in chapter 4. All right, so let's recap real quick. So we learned yesterday that friction is a force whose upper bound. Oops, let's get on screen there. Oh, I zoomed in yesterday. That's what it was. So the friction is given by this letter mu, which is the coefficient of friction, times the normal force between the two surfaces that are causing the friction, right? And technically, I wrote equals here, but technically it's always less than or equal. And that can be significant in some situations. And of course, this coefficient of friction has two varieties. There's the coefficient of static friction and the coefficient of kinetic friction. Static friction is the kind of friction that you have between two surfaces that are not actively sliding against one another. Whereas kinetic friction, that's the kind of friction that you have when the two surfaces are already sliding against each other. And the reason that matters is because if the two surfaces are not sliding, then the two surfaces have a chance to get all nice and snug and stuck together. And you can generate more friction that way than you can if they're already kind of skipping across one another. And so, in general, you'll find that the coefficient of static friction will be a larger number than the coefficient of kinetic friction. Either way, we expect the coefficient of friction for static or kinetic to be generally less than 1, but bigger than 0. And it doesn't have any units. It's a dimensionless constant. And it's going to relate just the size of the frictional force to how much normal force you've got. So again, we talked about all that last time. We kind of dealt through how to figure out the direction of friction and all that. At this point, we just need to put it to practice. We need to do some problems that involve friction. And let's start with, I guess, the kind of most basic problem there is. Let's figure out how to do friction, and heck, let's put it on an inclined plane because physicists love ramps. We love them. They're great. So imagine I've got a ramp, and let's have that ramp make a 30-degree angle with the horizontal. And what I'm going to do is I'm going to put some kind of object on that ramp. And let's start super simple. Let's just set the object on the ramp. However, this object is made out of a material such that the coefficient of static friction between this object and the ramp, let's have it be equal to 0.4, right? Whereas the coefficient of kinetic friction between that object and the same ramp is, let's go with half of that, 0.2. I'm picking those numbers for a reason because I'm trying to cook the books and make sure that this works. So here's my question. If I just set this object and put it at rest right there, and I let it go, is the object going to slide down the ramp or is it going to sit still? If it does slide, what acceleration is it going to have? All right. So those are the questions that I want to answer about this. And this is the only information I'm going to give you. I got a box, I got a ramp. That's all we know. Turns out that's going to be the only thing we're going to end up needing. So to think this through, let's think about this the same way we would do any other Newton's law problem, right? The first thing we're going to do is we're going to do a free body diagram, right? We're going to figure out what forces we've got. Now, obviously, this box is going to feel a force of mg pulling it downward. And it's going to feel a force from the ramp. That's the normal force, right? And that force is going to be perpendicular to the ramp, which is right there. And there's friction on this ramp. We haven't dealt with that before, but there's friction. And to know the direction of friction, you ask yourself, well, what would happen to the box if there weren't any friction? And that's pretty obvious. If there was no friction, if this ramp was slippery, this box would slide down the ramp. So friction is going to oppose that. So the force of friction is going to be parallel to the ramp, but up the ramp, like so. That's what we know. So I've got three forces acting on this object. There's nothing else touching it. There's nothing else pushing it. That's the whole shebang. So to solve this problem of will it slide, the first thing I'm going to do is let's figure out the acceleration of the box. Well, I've got my free body diagram. The next step is to choose a coordinate system and to break those forces up into that coordinate system. And because I'm on a slanty ramp, the trick for that is to choose a coordinate system that is also itself slanty. So I'm going to have my x direction roll downhill. I'm going to call the positive x direction down the hill and the positive y direction perpendicular to hill. Now, if I do that, then what's going to happen is when I break down the normal force into components, that's pretty easy. It's all going to be in the positive y direction. So it'll have a 0 I hat component, but a positive j hat component. Meanwhile, the friction, well, that's pretty easy as well. The friction is going to be given by, at most, mu times n. So let's go ahead and assume that my friction is at its maximum. We'll see whether or not that's true here in a minute. But let's assume it for the moment. Now, it's going to be up the ramp, which is in the negative x direction. So I'll have negative mu n in the x direction, but 0 in the j hat direction. That was pretty easy. For gravity, I got to split that into a y component there and an x component there. Again, that's perpendicular. And I know from having done this kind of problem before that if this angle here is 30 degrees, that angle there will also be 30 degrees. And that means that I can break that triangle down into components. Again, this is the x component. And you'll notice how the x component is the opposite side of the triangle from the angle that I know. Whereas the y component is here. That's the adjacent side of the triangle. And so from SOHCAHTOA, I know that the sine is opposite over hypotenuse. So This is going to be the total, that's mg, times the sine of 30 in the I hat direction. It's pulling it down the ramp, which is the positive x direction. So that's going to be positive. But the y component is into the ramp, which is the negative y direction. So it's going to be minus mg cosine of 30. And again, notice a lot of times you start to associate sine with y and cosine with x, but this is one of those situations where because of the angle that we know, it's the other way around. So don't assume cosine means x and sine means y. Draw the triangle. The opposite side will come from the sine, and the adjacent side will come from the cosine. And make sure you get that right in a given problem. It's going to be different. And I am notorious for writing questions that require you to know, and if you get it wrong, it'll screw you up. So I've broken them into components. That's the second step of every Newton's law problem. The third step is going to be to generate some equations. And I'm going to generate first my x equation. And in the x direction, I have three forces, this one, and this one. I'm going to write this one first because it's positive. So I'm going to have mg sine of 30 minus the coefficient of friction times the normal force. So this is the sum of the forces in the x direction. And that should equal the mass of the object times the acceleration of the object in the x direction. So far, so good. Now, in the y direction, I have three forces, this, and this. So when I add those together, I'm going to have this plus 0 minus this. So n minus mg cosine of 30. And that's going to equal the mass of the object times the acceleration of the object in the y direction. So those are my two equations that I'm going to be solving. And when I get to this point in a problem, I always will choose to pause and I'll ask myself, do I know anything at all about the acceleration of the object in this problem? And I do know a little something, right? I know that if this box moves at all, it's going to slide down the ramp, right? So there might be some acceleration in the x direction. It could definitely move in the x direction. But what it's not going to do is it's not going to go flying up off the ramp. That's stupid. It's not going to sink into the ground. That's stupid. So whatever it does, it won't be moving in the y direction at all, which means there cannot be an acceleration in the y direction. It just can't happen. So AY has got to be 0. Right? I know that from common sense. So now I have those equations to solve for, and I'm looking to see whether it will slide. And here's the idea. If I put this thing at rest, if it's sitting there at this moment not moving, if I have an acceleration of 0, that means that whatever state of motion it's in right now, it's going to keep that same state of motion. So if I have an acceleration of 0, then this stationary box will continue to be stationary. It will not slide at all. So clearly, if I solve for A and get 0, it didn't move. What happens if I solve for A, but I get a positive number? Well, getting a positive number means that it wants to accelerate down the ramp. That tells me that the forces of gravity pulling down the ramp are stronger than the biggest the friction could ever get. And in that case, friction cannot stop it from moving. It will slide down the ramp. Now, what would happen if I were to solve this problem and get a negative acceleration? Well, that would suggest that the force of friction, which is this term, is bigger than the part of gravity pulling it down the ramp, which is this term. And that would suggest that the box is going to try to slide up the ramp. But wait a second. That's never going to happen. You're never going to put a box on a ramp and suddenly friction is going to drag the ramp up drag the box up the ramp. That's not going to happen. So what will happen is if I get a negative value, what that means is that this force of friction I used was too big. Remember, it's not F equals mu n, it's F is less than or equal to mu n. So whatever number this is, the friction could always be less. And so what's going to happen is, imagine this term here equals 5, right? And this term here equals 10, negative 10. Well, obviously that would give me a negative number, 5 minus 10. Well, what's going to happen is friction will respond by just not pulling as hard as it has to. So if I get a negative number, what will happen is the friction will just pull a little bit less hard than it could, and it still won't move. So for this problem, if I get a positive acceleration, he's going to slide. If I get an acceleration of 0 or anything negative, that's going to suggest that the friction is strong enough to keep it from moving and it won't slide. So to answer the first part of this question, all I'm going to have to do is solve for the acceleration and see whether it's positive or negative. All right. Then if it's positive, I'll have to continue on and do this part. And hopefully I picked my numbers in such a way it's going to end up being positive because I really want to do this part. So let's think this through. I want to solve for A. The problem. I don't know what the mass is. I didn't tell you. I also don't know what the normal force is. Didn't tell you that either. So I'm going to have to solve this problem with 2 big pieces of missing information. But I'm not deterred because I've done this before. So the first thing I'm going to do is try to eliminate anything that I don't know. I'm trying to solve for A, so I need N to die a horrible death. And N occurs in this other equation over here. Oh, look, since N minus some stuff equals 0, if I just add that stuff to the other side, the normal force is going to have to equal mg times the cosine of 30. Neat. I can't get a number for that because I don't know what mass is, but whatever. I'm going to take this expression for N and plug it back up into here and get rid of N there. When I do that, watch what happens. So now I've got mg times the sine of 30 degrees. Let's get down here where you can see it. Minus mu, that's the coefficient of friction, times mg cosine of 30, that's the expression for N that we just found a minute ago, equals m times the acceleration in the x direction. Now, what's cool about that is you'll notice at this point, all 3 terms contain the mass of the box. I don't know what the mass of the box is, but if I divide everything by m, this m will cancel, this m will cancel, this m will also cancel. So as long as every term has the same variable in it, that term will cancel out. It won't be important. I don't even need to know the mass to know the answer to this question. So now you can see that my acceleration has been solved for. It's going to be g times the sine of 30 minus mu times g times the cosine of 30. Now, I got 2 different values for mu, right? The static coefficient of friction is 0.4. The kinetic coefficient of friction is only 0.2. So which of those 2 numbers am I going to use? Well, I'm trying to determine whether it slides at all. So if it doesn't slide, I'd be using static friction. So what I'll do is I'll use the static friction coefficient first and see if the static friction is enough to keep it from moving at all. Let's see. So when I plug that in, I'm going to have 9.8 times the sine of 30. Well, the sine of 30 is a half. So this term here is 4.9. Over here, I'm going to have 0.4 times 9.8 times the cosine of 30. And that ends up being only 3.39. And so you don't have to be a genius to know that 4.9 minus 3.339 is definitely going to be a positive number. And it doesn't even matter what that positive number is, because here's what's going to happen, right? I know this is positive. And remember, that means that even if the static friction is pulling as hard as it possibly can, it cannot overcome the force of gravity pulling it down the ramp. It's going to slide. But once it starts to slide, I'm not going to have static friction anymore. It's going to be moving. So it turns out that even if I were to subtract those two numbers, that won't be my answer. My actual answer is going to be higher than that, because once it starts to slide, the friction is going to get even wimpier. It wasn't strong enough to stop the box, and now it's not even as strong as it used to be. I use that instead. So my actual acceleration, I won't even use the 0.4. This was only important for seeing whether it slid to begin with. Now I'll go back, but this time I'll plug in 0.2 for mu. So now this is still going to be 4.9. That's never going to change. And that's going to be 0.2 times 9.8 times the cosine of 30. And that is going to be my actual acceleration. So there, if I take 4.9 minus 0.2 times 9.8 times the cosine of 30, I actually end up getting 3.2 meters per second squared. Super easy. So the idea here is that anytime you have a problem that involves friction, all you're going to have to do is treat it like any other Newton's law problem. The difference being that when you go to break down your forces, you're going to include a frictional force. That frictional force will be at its maximum mu times n. So you'll plug that expression into your force diagram and into your equations. And what's going to end up happening is, because the frictional force is always going to be perpendicular to your normal force, what will end up happening is you'll end up with your y component will probably have n in it, but your x component will probably have mu times n in it. So n will appear in both equations. And in order to solve it, you're going to have to use both equations. You'll use one equation to solve for n, replace that value for n in the other expression, and move on from there. That's the process. It's pretty straightforward. You guys can do it in your sleep. Let's do one more kind of friction example. This is one that I think I used to put it on the homework, and I haven't done it for the last couple of semesters, and I kind of miss it. But I like it because it's kind of non-standard. So let's imagine that I've got a wall, right? And what I'm going to do is I'm going to take a box, and I'm going to press it up against the wall. And this box has a mass of, let's say, 5 kilograms. And what I'm going to do is I'm going to push this box, but I'm going to push it diagonally with a force of some number of newtons. And I know that the wall has friction with that box. The coefficient of static friction, mu s, is 0.5. And what I would like to figure out is, what's the hardest amount of force that I can push with? In other words, what's the biggest that P could be and the box not slide? And also, what's the smallest value that P could be and have the box not slide? Either way, I want the box to not move, but that's going to give me a range of forces with which I can push that box and successfully pull that off. Now, it may not be obvious to you yet why I should have a range of values. So I'm just going to write that out. So let's think this through. Let's imagine that I am pushing so hard that if I pushed even a smidge harder, it would slide. Now, what direction would it slide if that were the case? Well, I'm pushing really, really hard. And so what's going to happen is I've got gravity pulling it downward. And if I push just right, the force of my push could cancel out gravity. I'm pushing up, it's pulling down. So even without friction, I might not be able to move it. If I push extra hard, though, what's going to happen is I would overcome gravity and start to slide it up. So if that's the case, the friction would want it to try to not slide up the ramp. And the friction would also be downward. So in that scenario, if I'm pushing super, super, super hard so that it would try to slide up the wall, then the friction would be helping gravity out by being downward. Now, there'd also be a force from the wall. That's a normal force. So in that situation, that might be my free body diagram. And if I solve for the value of P that makes this true, what I would be solving for is the largest value of P that I could possibly get, right? If I push any harder, it would slide and overcome the friction. So there's one scenario. Let's solve that one. We'll come back and figure out what's different for this one here in a minute. So just working it this way. I'm going to choose a regular boring coordinate system. Here's the positive X direction. Here's the positive Y direction. If I do that, breaking them down is pretty easy. The normal force is apparently only in the X direction. Oops, hello. Only in the X direction. So it's N I hat, 0 J hat. Oops. The gravity force is not in the X direction. It's going to be negative in the Y direction. The frictional force is going to be only in the Y direction, but not in the X direction. Now, this push that I'm pushing with is a little bit to the left and a little bit up. So it's going to have two components. And I got to push at some angle. Let's specify that angle. Let's say that that angle is, I don't know, 30 degrees. I like 30 degrees. So I'm pushing diagonally at a 30-degree angle. Notice if I change the angle, it would change my answer. And so now I'm going to break that push into two components. The adjacent side is going to come from the cosine. So it'll be whatever force I'm pushing with, which we're going to solve for, times the cosine of theta in the I hat direction. But it's to the left, so let's slap a minus sign on it. And then the Y component is going to be the opposite side, so that's going to be the sine. So P sine theta, J hat. It's upward, so let's make it positive. So those are my four forces broken down into components. Now when I go to generate some equations, in the X direction, I have two forces, this force upward and this force, or excuse me, this force to the right, this force downward, or to the right and to the left. Oh my God, I'm so tired. N minus B cosine 30 degrees equals the mass of the object times the acceleration in the X direction. In the Y direction, I have 1, 2, 3 forces. The 0 is going to not matter. This is upward. Let's write that first. So P times the sine of 30 degrees minus mg minus mu times n is equal to 0. So there's my expression. Oops, hello, equals m a y, not necessarily 0. So now when I get here, I have to pause and I have to think, do I know anything at all about the acceleration of this object? In the X direction, well, I know the object, if it moves, it's not going to move left or right, right? The wall won't let it. It's not going to go flying off the wall. There's no reason for it to, and it's not going to sink into the wall. So the x direction, I know for sure the acceleration must be 0 no matter what. In the y direction, it could be non-zero because I could push hard enough to make it slide up the wall or push weakly enough that it falls down the wall. So in principle, this doesn't have to be 0. However, if I'm trying to find the hardest force that I can push with and not move it, then I'm going to go ahead and force it to be 0. Hey, Roscoe, shut up. You're cool. You cannot help that our dog's obnoxious.
Stop, I'm here.
So in this particular problem, we're going to make it 0. I was just jumping the gun by assuming it without talking about it first. So I've got...
I'm sorry.
You're fine, sweetie.
It's not my fault.
He's just very excited.
I know.
All right. So
You're good.
lost train of thought. Oh, we're trying to solve this problem. I want to solve for P. P is what I need to find. I'm trying to figure out what force I could push with. I don't care, however, about N. So I need N to go away, but it shows up in both of my stupid equations. So let's kill N.
Really?
I notice, thank you, sweetheart. I notice that N appears up here. If I solve this equation for N,
You're too loud.
I will get that N is equal to however hard I push times the cosine of 30. I can then take that expression for N and pop it in right over here. And now what I'm going to have is P times the sine of 30 minus mg minus mu times P times the cosine of 30 is equal to 0.
I don't know why he's doing it.
He's obnoxious. All right, so there we go. I'm solving this little guy here. I want to get P by itself. So what I'm going to do is take everything that has a P in it, leave it on one side. Everything without a P, put it at the other side. So this has no P. Let's move that over. So I've got P times the sine of 30 minus mu times P times the cosine of 30 equals the mass of the object times G. I'm still trying to get P isolated. So what I can do is factor a P out of each of these two terms. And so now it's pretty easy because once I factor it out, I can just divide by all this ugly mess. And my final answer to this entire little fiasco looks like that. And conveniently, we were given both factors that we didn't know, right? We were told that M was 5 and the coefficient of static friction was 0.5. So I can plug in all my various values and we'll see what we get. We'll see how hard I can push. So here, sine of 30 is 0.5 minus half of the cosine of 30. That's 0.066 down here. And I'm going to take 5 times 9.8 is 49. So 49 divided by 0.066. I get 731 newtons. So as long as I'm pushing with less than 731 newtons, there's going to be enough friction to prevent the object from sliding up the wall. So we've solved half of the problem. I know as long as it's less than 731, it won't go sliding up the wall. So 731 is the largest force that I can push with. But what about the smallest force that I can push with? Well, imagine that I don't push at all, right? If P was 0, if I don't push at all, then what's going to happen is the box wants to slide down the ramp. Imagine there's no push and no friction. It would definitely fall, right? So if I'm not pushing at all, friction would want to prevent it from falling. So what would happen is the friction wouldn't be downward, it would be upward. I'll have the exact same problem, but with a slightly different free body diagram. Now what's going to happen is friction has reversed to try to prevent it from falling. Gravity is trying to make it fall. And I am still going to push, but I'm going to push with a wimpier force to try to help gravity or try to help friction keep it from falling. So in the previous problem, the friction and the push and I were at odds. Here, the friction and the push are working together. Now, what's going to happen is this problem is going to practically solve itself because it looks very similar to what we had before. Like all that has changed is we just flip that arrow upward. But that means that when I go to break down all of my forces, the normal force, same as it used to be. The weight, same as it used to be. So that's the same. Heck, even the push. The push is the same as it used to be. All that's going to have to happen is this. We're going to make that be positive. It's going to be upward, not negative. But that means to solve this problem, all I've got to do is, boop, there we go, it's plus now. But that means that when I go do my equations, I'm going to have the exact same two equations except, boop. But if that's positive, well, that never changed. So I got this is still the same. I'm plugging that in. So this is still the same except, boop. You got to make that noise, by the way, when you do this. Boop. So literally all that's going to happen when I go and solve this problem is I'll have the exact same answer, except that. This is why I don't plug numbers in until the very, very end, because if I plugged in numbers at this step, I would have had to go through and do all this garbage again, right? That's too much work. If I do this generically, all I had to do was make a real quick change, and now I could just reevaluate my answer, and it's super easy. Because now what's going to happen is it's going to be the sine of 30 plus 0.5 times cosine of 30. So the denominator is going to be bigger now, 0.933. So 49 divided by that. Hello, 49 divided by is about 52.5. That's a pretty huge range, right? So if I push with less force than this, then what's going to happen is I'm not helping the friction enough, and the gravity is going to be sufficiently strong that it's going to drag it down the wall. But if I push harder, friction will reverse, and as long as I push with less force than this, it won't move at all. If I push with more force than this, it will slide. So anywhere in between, the object would be stationary, and the friction would just adjust to be whatever it had to be to exactly cancel out all motion and keep it from moving. Super easy. We can do this in our sleep. So that's the force of friction. It's, pretty important. I can guarantee you there'll be a friction force problem on, your second exam, and there's always going to be one on your final exam. I expect you to know how to do this stuff, but it's not hard. Now, friction is an example of what we will learn later to be what we call a dissipative force, a non-conservative force. And we'll learn what that means in a couple of chapters. But there's another dissipative or non-conservative force that we can deal with from time to time. And in a lot of ways, it's sort of similar to friction. and that's air resistance or viscous drag. How is air resistance similar to friction? Well, if I have an object sitting on the ground and I drag it across the ground, the friction will always oppose that motion. So when I drag it to the right, friction pulls to the left. When I drag it to the left, friction pulls to the right. So what's going to happen is, friction always opposes motion, and the drag force is similar, right? If I move an object through the air, in order to move that object around, I've got to push all the air that's in the way out of the way. And you don't normally think about air being a thing you have to move, but that's because if I just kind of move around at slow speeds, the air pushes back on me with such a small force, I barely notice it. However, I know that it's there, and if I were driving my car down the freeway, traveling, 60 miles an hour, and I stick my hand out the window, I'm going to feel the air against my hand there. I'm going to feel the force that I have to push with to get the air out of the way as my hand moves through. So whatever direction I'm traveling, the air is pushing me back the other direction, very much like friction. So when we talk about the drag force or the force of air resistance, it's similar to friction in that it always opposes our motion. Right? And so what's going to happen is we're going to have to model this force. But what's going to happen is the drag force is going to depend on a number of factors. It's not always going to be the same for all objects. And here is the relationship. I'm just going to spell it out. At high speeds, that's the function that we would use to describe the viscous drag force. Now, what the heck does all this mean? Well, the obvious easy part, right? D is obviously the force. That's going to be the force of drag in newtons. The other obvious thing is V. V is the velocity. Now notice, because this goes as V squared, what that means is that if V is very, very tiny, if V is small, well, V squared is also small. Like 0.5 squared is 0.25. It's even smaller, right? But as V gets larger and larger and larger, the force is going to get bigger and bigger and bigger. And in fact, if you double how big your velocity is, your drag force is going to quadruple. So the drag force is going to get larger quadratically in terms of your speed. That's why at low speeds you don't notice it, but at high speeds it becomes more and more and more noticeable. That makes sense. Now, what's perhaps less obvious, this variable rho, that is going to be the density of air. And I say air, but I should probably be a little bit less specific, because it turns out that this same formula would work if I'm traveling through water or through some other gas or any kind of fluid. Fluids or liquids, or what I mean by liquids or gases of any kind. This same expression is going to work. Now, why should the density of the fluid matter? Well, because if I'm moving my hand through the air, I got to push the air out of the way. I got to exert a force on the air. And remember, F equals ma, right? So the more mass that air has, the more force I'd have to push with to get it out of the way. The harder I push the air, the harder the air pushes back on me. So having a more dense fluid where there's more mass to push out of your way means you're going to have to fight harder to get through it. So in practical terms, it means that as the air density is increased, it's harder to push out of your way. That's also why, like, if you try to run in a swimming pool, it's crazy hard, right? Because the mass of the water is quite large, and you're going to have to push that out of your way as you move. That's very difficult. So that's why the density shows up here. Now, A is called the cross-sectional area. Now, what do I mean by cross-sectional area? If you guys are in a biology class, like Gupta's anatomy class or whatever, you probably end up seeing a lot of cross-sectional diagrams. And a cross-sectional diagram is the kind of thing you often see in an anatomy textbook. Give me a second. And the cross-sectional diagram is like where they show you a picture of the body, but you've basically you've sliced the front off and you've cut it away, and you end up seeing like a diagram where you can see like all the internal organs. That's what a cross-section is. You slice it and you look at kind of the silhouette that it leaves behind. And that's a way to think about it here. The cross-sectional area is the area that the air sees as you move through it. So imagine I've got this box, right? This box of markers. If I'm taking this box and I'm moving it around, then what's going to happen is the air is going to have to get out of the way. But if I move the box towards the camera like this, what's going to happen is all the air in front of this has to get out of the way. The area that the air sees is the area of this box, right? But what if instead of moving it like this, woo, extreme close up, I instead rotate it like this and move it like that? Well, now what's going to happen is there's only this much air that has to get out of the way. There's less air it has to push out of the way. So the area that the air sees is this area, right? If I, move it this way, it'll see this area. So it's the area that the air is facing as you move. And so if I'm dropping this box from the like from a skyscraper or something, the amount of drag I'm going to get is going to be larger if I drop it with the long side down. It's going to be smaller if I drop it with the narrow side down, right? I'm going to get a different amount of drag depending on how I drop it. And so that is why we deal with the cross-sectional area. It's going to depend on the shape of the object as it's presented to the air. And then the last part is this. This is called a coefficient of drag. So the coefficient of drag is just a number. It's kind of like the coefficient of friction, in fact, in that it's a dimensionless number, has no units. It's usually less than 1. And it's a measure of the degree of aerodynamicness of the object. It depends on the shape of the object. So, I need that onion, it's going to die. What's going to happen is different shapes are going to have different coefficients of drag. If you look in your textbook in chapter 5, there's a chart, and that chart lays out the various coefficients of drag you see for different shapes. So I haven't memorized that chart. I know that like a spherical object has a coefficient of drag of about 0.45, right? That's a number you don't have to memorize, but you can look it up. A boxy shaped object is going to have a different coefficient of drag. The more aerodynamic it is, the smaller that number will be. If you go and you buy like a new Corvette, like Corvettes are made to be aerodynamic because you want to be fast, right? If you want to be fast, you want to reduce how much air pushes back against you as you drive. The coefficient of drag on a Corvette is somewhere in the neighborhood of 0.2, right? If you go and you buy a Volvo, right? Volvos are renowned for being kind of boxy and not super aerodynamic. It's going to have a coefficient of drag closer to 0.4. So bigger numbers, less aerodynamic. That's all it means. So this is how you would determine the force of air resistance acting on an object. Now, there's good news and there's bad news about this coefficient of drag formula. And the good news, well, the bad news is it depends on your velocity. And boy, is that a pain in the butt. Imagine that I do something simple, like I'm a dude and I've jumped out of an airplane. Here's a dude. Oh God, I've jumped out of an airplane. What are the forces acting on this dude? Well, gravity is going to pull this dude down. And as he falls through the air, the force of drag is going to push him up. Now, if you do F equals ma on this guy, it'll be the upward forces minus the downward forces. So the net force would be the drag force minus mg, and that's going to equal his mass times his acceleration. Now, when he first starts to fall, if he starts with a velocity of 0, well, remember the drag force looks like this, right? If my velocity is 0, doesn't matter what the rest of the stuff is, the whole thing is 0. So at the moment where he first starts falling, this drag force starts out being 0. Now, if the drag force is 0, I have negative mg equals ma, the m's will cancel, and I'll get a equals negative g, which, no duh, if you are falling, your acceleration is going to be negative 9.8. That's what you expect. And that's why, up until now, we've always ignored the force of air resistance, because as long as you're at a low speed, your acceleration is going to be the acceleration of gravity. But what's going to happen is as you fall more and more and more, your velocity is going to get larger and larger and larger. This is going to stop being 0. And now what's going to happen is your acceleration is going to get smaller and smaller and smaller. It's going to start off at 9.8, and it's going to get smaller as you go. So your acceleration, as a function of your velocity, you would expect it to be 9.8 all the time if there was no air resistance. But because air resistance is there, it's going to start off at 9.8. It's going to decrease over time. Right? That's what we're going to expect to see happen. It's going to decrease quadratically because that's squared. So it'd be like a parabola. But here's what's tricky about it. If I wanted to figure out things like how long it takes me to fall from my airplane when I jump out with my parachute or whatever, that's difficult because the acceleration is going to keep changing constantly. It's going to start off at 9.8, but after a while, it's going to get more and more and more and more different from 9.8. And because it's changing continuously, in order to solve the problem of like how long does it take me to fall, I'd have to use calculus. It's too complicated for this class, right? People can do it. I've done it before, but we're not gonna. And it's all because my acceleration depends on my velocity, but then my velocity keeps changing, so my acceleration keeps changing, and all my equations of motion that we learned in chapter 2 only work for constant acceleration. So that's tricky, right? That's a hard problem to solve, and it's beyond what we can do. So I can't really do that problem. What I could do, however, is I could imagine what's going to happen as this guy falls faster and faster and faster and faster, right? I know that his acceleration is going to start off at 9.8. It's going to get lower and lower and lower and lower. At some point, it's going to get so low that his acceleration is going to become 0. Now, when that happens, when his acceleration becomes 0, well, that means his velocity stops changing. Once your acceleration gets to 0 like this, whatever velocity you've got, you're going to keep it. It's not going to change anymore. We call that terminal velocity. So an object at terminal velocity doesn't accelerate at all. It just keeps falling at a constant speed. And it'll happen once you get going fast enough that the drag force pushing up is equal to the force of gravity pulling you down. It explains a lot. right? It explains why if you take a brick and a feather and you drop them side by side, the brick and the feather don't hit the ground at the same time, right? Because what's going to happen is the terminal velocity of that feather ends up being a really tiny number. It falls at 9.8 at first, but very quickly it's going to hit some maximum speed where the drag force pushing up is equal to the tiny little feather weight, and the acceleration becomes 0. And so most of that trip down, the feather is dropping at a constant velocity. Whereas with the brick, it never hits its terminal speed. It's so heavy that the drag force never even gets close to stopping it. In fact, this is so much bigger than this is basically negligible, and the brick falls at about 9.8 the whole way. It never falls past this region. And that's why, feathers fall more slowly than things. It's because they hit terminal velocity faster. How would I know what something's terminal velocity is? Well, I'd make the acceleration be 0, and then I'd solve for the velocity that makes this equation true. Well, if d equals this, I've got 1/2 CA rho v squared minus mg is equal to 0. I want to get v by itself, so I'm going to add this to both sides. I'm going to multiply by 2 to get rid of that 1/2. I'm going to divide by CA and rho. And then I'm going to square root both sides. So the terminal velocity of an object is given by that expression. And so you can see that this is how fast you have to be going when you're falling when you stop accelerating at all because of air resistance. And the bigger your mass, the smaller your terminal velocity. So feathers, they have a small mass. That's going to make v very small. It also depends on the area. The bigger your area, the more you're dividing by, the smaller your terminal velocity. So feathers have both a tiny mass and a really big area. They hit terminal velocity in hardly any time at all. And that's why they fall super slowly. Whereas that brick has a pretty big mass and a pretty compact area, its terminal velocity is going to be quite large. If I'm a dude jumping out of an airplane, terminal velocity for most humans is somewhere in the neighborhood of about 200 miles an hour. Now, it's going to depend on some stuff, right? It depends on how the person is oriented while they fall, right? If you've ever watched skydivers, where sometimes they'll get in a plane and they'll all jump out one at a time, and then as they're falling, they'll link up and make like little snowflake patterns with their bodies as they fall. You know what I'm talking about? Well, if you think about that, how does that even work? The guy who jumps out first, he's picking up speed the entire time he's falling before the guy above him even drops out. So let's say this guy falls for 1 second. He's going to have a velocity of about 9.8 meters per second by the time this guy who has a velocity 0 jumps out of the plane. So now he's got a velocity of 0. He's got a velocity of 9.8. Since he's going faster, he's pulling ahead. So as they fall, they should be getting further apart. And what's going to happen is the guy in the front's always going to be traveling faster than the guy in the back. He's always going to be pulling away. So if there was no air resistance, there's no way that the people who jumped out later could ever catch up with the person who jumped out first. But what happens is the guy who jumps out first, he goes spread eagle. He spreads himself out as much as he can so that his cross-sectional area is as large as he can make it. That makes his terminal velocity comparatively slow. And he'll hit terminal velocity, he'll start to slow down, and he'll fall at a particularly constant piece of rate of speed. Now, the guys who jump second and third, what they're going to do is instead of going spread eagle and trying to make their cross-sectional area big, they're going to drop head or feet first. They're going to fall like a missile. So their cross-sectional area, instead of it being like the entire side of their body, it's like just the front of their body. They make this very, very tiny. And as a consequence, their terminal velocity is quite large. So while the guy who dropped first is traveling slowly, they're continuing to accelerate until they catch up with him. Then they go spread eagle too, so they can match terminal velocities as they fall the rest of the way down. So that's how that works. And of course, when they eventually pull the ripcords on their parachutes, how do parachutes even work? What's the point of a parachute? Well, when you pull that ripcord, what happens? That parachute on your back blossoms out and becomes very, very large. So suddenly your cross-sectional area has gone from human body cross-sectional area, which is pretty small, to giant parachute cross-sectional area, which is quite large. Plus, it's this like weird scoop shape. The scoop shape is not very aerodynamic. It tends to trap air in and makes it hard for the air to get out. So the coefficient of drag of that parachute shape is way, way higher than the coefficient of drag of your human body shape. So when you pull the ripcord, you're making C and A both get really, really big. That means your terminal velocity gets very, very small. And if you're traveling faster than that, what will happen is the drag force will momentarily be larger than the force of gravity. It will slow you down until you reach that tiny slow speed. And if your parachute is well designed, this terminal velocity is going to be slow enough that when you hit the ground at that speed, it doesn't cause any injury to you. That's the idea. So when it comes to terminal velocity, I can't ask you a lot of dynamics questions about terminal velocity simply because we don't have the calculus for it. But I could totally ask you about terminal velocity problems. So you should know how to solve for terminal velocity. Or if I said, find the acceleration when you're traveling a particular speed, you could solve that. All you have to do is solve for A at a particular speed. You could totally do that. But that's how drag forces work. And it's pretty straightforward. One of my favorite little stories when it comes to the drag force is something that I learned from my undergraduate physics textbook. And I love this story. I tell it every year. So at the beginning of every chapter in my undergrad textbook, they always started with kind of a, isn't this interesting kind of factoid to try to capture your interest. And then they talk about like what the physics was during the course of the chapter. Well, the beginning of our chapter 5, there was a story about cats falling out of windows. So it turns out every year, hundreds of cats fall out of windows of tall buildings. Maybe the windows are open, they jump out. I have some friends who live in Seattle where I guess it's cool enough most of the time they don't even have air conditioning in a lot of the big high rises. And they lived on like the 17th floor. And they were always in fear during the summer that they'd open up the windows and their stupid cat would jump out and fall to his death. So they'd have to lock the cat up into another room when they opened the windows in the summertime. Now, imagine you're a cat and you've just made that poor life decision of jumping out that window. And ask yourself what's going to happen. Well, here you are, you're a cat, you jumped out. And at first, you're not traveling very fast. So this is basically zero. So at first, you're falling with an acceleration of 9.8 meters per second squared. Now, if you've ever ridden a roller coaster or just driven over a hill too quickly, sometimes you'll get that weird, funny feeling in your tummy where you kind of feels kind of queasy. What that is your body's accelerometer. You can tell that you're being accelerated because you feel that weird sensation in your body. And a cat's going to feel that as well. So this cat has just jumped out of this window. And at first, it's going to feel that weird queasy feeling. It's going to freak out, right? Oh, God, I'm going to die. And so what's the cat's natural response to feeling it's about to die? They huddle up. Now, when they huddle up, what's happening is they're making that cross-sectional area very tiny. That's going to make their terminal velocity pretty high. But true story, if you look at the statistics for the death rates of cats who undergo this process, what you're going to find is that, you know, cats that jump out of like the second story window, they die a certain percentage of the time. Cats who jump out of the third story window, they die a slightly larger percentage of the time, which makes sense because they're falling further, right? Fourth story window, they tend to fall they tend to die even more than the ones who jumped out of the third story window. As you go up in floors, the death rates keep climbing, which makes sense, until you get to about the fourth or fifth floor. You go beyond that, all of a sudden the death rate starts to drop. And you're like, how is it that a cat that jumps out of the 10th story window could have a better chance of surviving than somebody who jumped out of the 3rd-story window. That makes 0 sense until you think about it in terms of terminal velocities. Because what's going to happen is if you're falling out of one of those lower windows, you're not falling for very much time. You don't have time to build up speed, so you maybe don't ever hit your terminal velocity, right? But if you're falling out of a high enough window, what's going to happen is the cat falls out and he's speeding up, speeding up, speeding up, speeding up. But eventually, if it's falling for enough time, it will hit its terminal velocity. Now, that terminal velocity was determined by it going, oh God, I'm going to die. But when you hit terminal velocity, you stop accelerating. And when you stop accelerating, that weird, funny feeling in your stomach goes away. So if you're a cat and you're in that situation, what's going to happen is as you fall, that feeling goes away. The cat's like, it's not so bad. I'm not quite as freaked out as I used to be. It relaxes. And when they relax, they spread out a little bit, stretch out, get kind of prepared to land. But when they do that, their cross-sectional area just got way bigger. So now the terminal velocity of that cat goes way down. And usually they're even traveling faster than the terminal velocity. It's kind of like they became their own kind of almost minor parachute, and they slow down a little bit. They'll slow down until they reach that new, slightly slower terminal velocity. And so what will happen is those cats that hit that slower terminal velocity, they're going to hit the ground going a little bit slower than some of the cats that fell out of lower windows and never hit terminal velocity. And that's why all of a sudden their death rates go down a little bit, is they have time to hit a terminal velocity, slow down, and end up hitting the ground slower than the ones who jumped out of the lower windows. It's counterintuitive, but the statistics bear it out. It's kind of crazy. So that's the drag force. Now, there's one last section that gets dealt with in Chapter 5. Chapter 5 deals with stress and strain. And I kind of waffle about this. Sometimes I'll include it, sometimes I won't. It's summertime, and in the interest of time, I'm not going to cover those sections from Chapter 5. So on Monday, we will come in and we'll hit Chapter 6, where we're going to introduce circular motion. But in terms of Chapter 5, the only new things that it provides us are how to deal with friction, how to deal with the drag force. But other than that, it's basically just a continuation of Chapter 4. All the problems are going to get solved in the exact same way. Do a free body diagram, identify your forces and break them into components, generate some equations, solve the equations. Same 4 equations, same four steps. All you're doing now is you're including a couple extra forces you didn't know about before. All right, so I'm going to leave it at that, guys, and have a good day. I'll see you tomorrow. And again, the exam is going to be up a little bit later than I intended because I'm dealing with the technical issues of how do you get your lockdown browser installed, and that is not it doesn't work the way I thought it did. And I'm trying to figure that out. So I don't want to jump the gun on that. So the exam is going to get pushed back. It will probably not be due Friday. It'll probably be due either at the end of the weekend or even on Monday. But I'll let you know when I post it. Have a good one. See you later.